Hi, my name is Soroush Abbasi. I'm presenting our work SimA, Simple Softmax-Free Attention for Vision Transformer. This is a joint work with Pirsiavash. Vision transformers revolutionize image representation through incorporation of self-attention mechanism. These models have found widespread application across various domains. In greater detail, self-attention operates by taking the product of query and key matrices, yielding the attention matrix of size n by n, where n represents the number of tokens. Self-attention employs softmax for normalizing the n by n attention matrix. It's important to note that softmax utilizes the exponential function, resulting in a hn square calls for exponential in the attention module, where h represents the number of heads in multi-head attention. Subsequently, the output of self-attention module is computed by multiplying the attention matrix with the value matrix, and it is further processed through a projection layer at the end. There are dn square multiplication requires to compute the attention matrix, and additional dn squared multiplication to calculate the output matrix. In scenarios with a large number of tokens, such as high-resolution images, the self-attention module becomes computationally expensive due to the quadratic nature of multiplication with respect to the number of tokens. Attention module utilizes softmax as a normalization function, involving calls to expensive exponential operation. The computational cost of exponential operation is generally high, particularly on smaller devices with limited processing capabilities. For instance, exponential operation is considerably more expensive on FPGA compared to basic multiplication or addition operations. Furthermore, self-attention module exhibit quadratic computation with respect to number of tokens, adding to the computational demand. To overcome these limitations, we introduce our simple attention module named SimA. We believe that softmax acts as a normalizer for attention values, making them comparable. In our approach, we replace softmax with a simple L1 normalization of each dimension independently. In both query and key matrices, each row represents a token and each dimension corresponds to a feature channel. We apply L1 normalization independently for each channel. In other words, we perform L1 normalization per column. We perform L1 normalization for both query and key matrices, denoting L1 normalized key and query as Q hat and K hat respectively. Subsequently, we compute the output of the attention module through a straightforward multiplication of a query, key, and value. Moreover, during both training and inference, we have the flexibility to opt for a computational linearity in either n or d, depending on the number of tokens. If n surpasses d, or in a simpler term, if input has high number of tokens, our approach involves multiplying k transpose and v first, then followed by multiplication with q. When n is less than d, or put it differently, if the input has a small number of tokens, our strategy involves multiplying q and k transpose first, then followed by multiplication with v. SimA offers two significant advantages over prior attention modules. First, SimA exponential free, resulting in a hardware-friendly design for our attention module. Second, during both training and inference, we can dynamically switch between the order of Q, K, V matrices multiplication based on the number of tokens. We conduct a comparison of execution time for a single block of SimA with vanilla attention across different hardware settings, including NVIDIA Nano, Apple M1 chip, and Raspberry Pi. SimA outperforms other methods in terms of speed, and we attribute this advantage to reduce computational overhead of exponential function. In evaluating its performance, we replaced the original attention mechanism with SimA in three well-established vision transformer families: DIT, XCIT, and CVT. We conduct supervised ImageNet classification training from scratch using SimA attention block. SimA achieves comparable accuracy to vanilla attention module, all while being free of exponential operation. Additionally, we eliminate all exponential operation by replacing GELU with ReLU in MLP layer, achieving accuracy on par with the original results. We know that in vanilla attention, multi-head outperforms single-head. We believe the reason is that in single-head, one dimension can dominate the whole dot product. In multi-head, this domination will be limited to one head only, leaving the other dimensions functional. In our experiments, there is a 2.8 point drop in accuracy for DIT with single head instead of multi-head. In SimA, we normalize each dimension independently. So unlike vanilla attention, SimA performs well in both single head and multi-head settings. We extend our evaluation of SimA to detection and segmentation tasks. First, we pre-train a vision transformer with SimA and ImageNet. Then, we fine-tune it with MS-COCO dataset. SimA showcases accuracy on par with vanilla attention. We train self-supervised learning method Dino with SimA attention block and ImageNet unlabeled training set. SimA achieves accuracy comparable to vanilla transformer models, all while eliminating the need for exponential operation. Since we multiply Q hat and K hat directly with V, the magnitude of Q hat and K hat should identify the important tokens, as we shown on the right figure. For this figure, we extract Q hat and K hat from layer 12 of transformer. Then we get L2 norm of each token for Q hat and K hat, and then we overlay it as a heat map on the image. In conclusion, SimA stands for Simple Attention Block. It is designed to eliminate the need for exponential operation, thereby reducing the computational cost of transformers, especially on edge devices. It also incorporates normalization and key and query matrices before multiplication, allowing for dynamic switching between order of d squared n or dn squared based on number of tokens. Thank you for your attention. Please read that paper for more details.